All right, today we're going to step into a pretty fascinating and, well, invisible world. We're talking about clean rooms. This is a place where the battle against microscopic enemies isn't one with walls or chemicals, but with a force you can't even see, the air itself.
It really does sound like a riddle, doesn't it? I mean, how can air, the very thing that carries all the dust and junk around, be the key to creating a totally sterile environment? That's the exact puzzle we're going to solve right now.
So, first, we got to meet the enemy, contamination. And we're talking about really tiny, unwanted particles. Dust, microbes, even skin cells. Stuff that's totally harmless to us day to day. But if you're in a pharmaceutical lab or a microchip factory, a single one of these little guys can destroy millions of dollars worth of products. No joke.
Okay, so how do we fight this invisible enemy? Well, you fight an invisible enemy with an invisible force. The secret weapon in this whole operation is just the clever manipulation of air pressure. It's such an elegant solution to a really tricky problem.
The physics here is actually beautiful. It's so simple. Just picture a super crowded room. That's high pressure. The second the doors open, what happens? People just naturally push their way out, right? Now think of an almost empty room. That's low pressure. When those doors open, people from the crowded hallway are basically pulled in. So high pressure pushes, low pressure pulls. That simple principle, it's everything.
And that one simple idea gives us three brilliant strategies. What you're looking at here are the core designs for a pharmaceutical airlock. Now, they might look kind of similar at first glance, but trust me, each one has a completely different mission. Let's break them down.
First up, we've got the Cascade Airlock. You can think of this one as the ultimate guardian. Its one and only job is to protect the super clean, super important room.
Okay, so pay close attention to the arrows here. You'll see what I mean. The air is always moving in just one direction. It goes from the outer gowning room, flows through the airlock, and then into the final clean room. It creates this perfect one-way street for air.
So how's it do that? Well, it's a pressure gradient, this cascade effect. The gowning room has the highest pressure. The airlock has a slightly lower, kind of medium pressure. And then the clean room? It has the lowest pressure of all, so any stray particles are constantly getting pushed away from that clean room back toward the entrance.
So at the end of the day, the Cascade Airlock's entire purpose is to form an invisible barrier, making sure nothing, and I mean nothing, from the outside world can drift into that pristine environment. This is exactly what you'd find guarding a multi-million-dollar microchip factory.
Okay, now let's check out our next design, the bubble airlock. Now here the focus totally shifts. It's not about protecting the room anymore. It's all about protecting the precious cargo that's passing through it.
Now look closely at this diagram. The highest pressure, see it there with the plus, is now right in the middle, inside the airlock itself. The rooms on either side are at a lower pressure, and this creates a protective high-pressure bubble.
See how the arrows are pointing outwards in both directions? The high-pressure air inside that airlock is constantly pushing out towards both the production area and the clean room. It's like an invisible force field that just radiates from the center. So the mission here is completely different, right? The bubble airlock is designed to protect something sterile while it's temporarily inside. Just imagine this is the system you'd use when you're transferring a fresh batch of life-saving vaccines. You're making sure nothing from either room can get in and contaminate it. And that brings us to our final design, the sink airlock. Now this one flips the whole script. Its job isn't to keep things out, but to trap something dangerous and keep it in.
So here, the pressure logic is the complete opposite of the bubble. The airlock in the middle actually has the lowest pressure. It acts like a drain or a sink. Just notice how the arrows show air from both the gowning room and the lab area rushing inward.
You've got high pressure in both of the surrounding rooms, and they are constantly pushing air and any potentially hazardous particles into that low-pressure airlock. It's basically an atmospheric trap, making sure nothing that's inside that airlock can possibly escape.
And that is its absolute critical mission, containment. This is something that's vital in, say, a high-level biosafety lab, where researchers might be handling a dangerous virus. The sink airlock makes sure it stays trapped right in that central zone, protecting everyone on both sides.
So there you have it. 3 airlocks, 3 very different jobs, and they all use the exact same fundamental principle. You know what? Let's put them side by side to really lock in the differences. Yeah, this table just makes it crystal clear. Cascade pushes air away to protect the room. Bubble pushes air out from the middle to protect the product inside. And sink
pulls air in to contain a hazard. It just goes to show you, choosing the right design is absolutely critical for the mission. And, that really just sums it all up, doesn't it? These systems are completely invisible. You could walk through one of these and have no idea about the complex physics that are at play all around you. It's a perfect example of elegant engineering that quietly makes modern medicine and technology possible. Which kind of leaves us with one last thought. We just saw how simple air pressure can be engineered to do these incredible things. It really makes you wonder, right? What other invisible forces are being cleverly harnessed all around us in ways we don't even notice?